we have to find the equivalent resistance between the diagonal points of a face, let's say if we see this is the top face, between A and C, that makes the diagonal of this face. So we have to find the equivalent resistance between A and C. Obviously this is going to be same for every face, because over here all the edges of the cube, they have the same resistance. So we are interested in finding what is the equivalent resistance between A and C. Once again we say that is current enters over here and it exits from here, from point C. When it enters over here, it has three options. One option, second option, third option. We obviously see that is this option and this option, they are same. So when we say the current enters from A, the first thing is look out for the shortest path. Once we look out for the shortest path, then we can say whether these paths, they are going to be identical, they are going to be symmetrical or not, whether the current is going to divide it equally or not. So once we have identified the shortest path, then we look out for the resistances, whether they are same resistances or not. And on the basis of that, we can say whether the current is going to divide equally or not. So when the current enters over here, the shortest path for this option and this option is 1 to exit. For this, 1 to exit. And all the resistance, they are equal to R, but not for this 1, 2, 3, 4 exit. So it means the current in this arm AB and AD is going to be same. Whereas in this arm AH, it is going to be something different. We are not bothered about the values. We are working on number one, we are looking for the shortest path. Then we see that is whether the resistances, they are same or not, whether the current come across the same kind of resistance or not. Then if it is, we look out for the points which are at the same potential, we join those points and then we try to find out the equivalent resistance. So over here, the same current is flowing in the arm AB and the same amount of current is flowing in arm AD. So it means D and B, they are at same potential. That is this D and B, they are the same potential. Similarly, when the current reaches over here, then once again it divides. It divides in such a manner that the same amount of current will flow in this wire and the same current will flow in this resistance. The shortest path is 1, 2, 3 exit, and for this also 1, 2, 3 exit or 1, 2, 3 exit, any path you can take. That is the same current will flowing in this and the same current will flowing in this arm. So it means if this is at one potential, the drop across this and drop across is going to be same. It means G and H, they are going to have same potential. If this and this, they are at same potential, so once again we can collapse them. D and B, they will join together, and similarly at the bottom face, E and G, they are going to join together. So if we collapse the upper face and lower face, it comes like this. A is here, D and B, they get collapsed, they are here, C is over there. For the bottom, H is here, E and G, they get collapsed, F is here, C and E, this and this, these two resistance, they are over here, A and H, they are over here. We have to find the equivalent resistance between A and C. These are points. This can be redrawn like this. R and R, they are parallel, so that makes R by 2. This and this parallel, that makes R by 2. This is R and R. These two resistors, they are parallel, so that makes R by 2. The same thing goes for these two resistors, R by 2, and for these resistors, R by 2. R by 2 and R by 2, now they are in series. This and this, that is in series. R plus R by 2, that makes 3R by 2, and this also makes 3R by 2. This is R by 2, this is R by 2, and this is R by 2. Now over here you see that there is a balanced Wheatstone bridge. That is, this by this is equal to this by this resistance value. So it means we can easily remove it. Reason being, when there is a balanced Wheatstone bridge, this and this point, they are the same potential. Potential difference is equal to 0, there will not be any current. So whether there is some resistance or not, that doesn't matter. Even if you join it, the equivalent resistance will still come out to be same. But anyway, over here we see that these two, they are in series, these two they are in series. R by 2 plus R by 2, that makes R. 3R by 2, 3R by 2, they are in series, that makes 3R. So now we solve it to get equivalent resistance as 3 by 4R. So this is how we can find the equivalent resistance in case of cubes, and we can apply the same concept in other networks also, where we can join the points at the same potential and subsequently we can find the equivalent resistance.